It's nice to meet each other in our fifth examination type question. My name is Tapio Komore, as you already know. So now let us see what's happening with that question, which is written question number 8. It reads, the cell notation of a standard galvanic cell containing an unknown metal electrode X is shown below. We have our X in solid form being converted to X3 plus at a concentration of 1 mole per cubic decimeter, and then we have our lead 2 plus at 1 mole per cubic decimeter being converted to lead solid. So now our question 8.1 says, name the component of the cell represented by the double vertical lines in the above cell notation. So since this one is a cell notation, this double line represents the solid bridge. Right? Our question 8.2, of course this one is a galvanic cell, so we actually know that in a galvanic cell we have our solid bridge separating our anode and cathodic reactions. Right? So question 8.2 states the two standard conditions that are applicable to the lead 2 plus lead half cell. Right? Our lead 2 plus, this one is an ionic solution. As you can see, it is at a concentration of 1 mole per cubic decimeter. So one of the standard conditions is that we are supposed to have a temperature, we are supposed to have a concentration of 1 mole per cubic decimeter. And then the other condition which we are supposed to satisfy is the temperature of 25 degrees Celsius or 298 kelvins, right? And don't be tempted to actually write pressure of 1.3 kilopascals or 1 atmosphere, because here we don't have gases. That one is only applicable to gases. So we have a temperature of 25 degrees Celsius or 298 kelvins and a concentration of 1 mole per cubic decimeter as our conditions for question 8.2. Then the question 8.3 says, identify the oxidizing agent in the above cell. Right? First of all, there is need for us to define what is an oxidizing agent so that we can identify it in the what? In our cell. So an oxidizing agent is a substance that causes the oxidation of another substance and is itself reduced in the course of the reaction. So which means to say that an oxidizing agent itself, we can identify it from a reduction reaction. So in the reduction reaction we are adding electrons. So let us see in our question 8.3 and see what we can actually derive, how we can derive our oxidation, our oxidizing agent. So in our 8.3 we are saying that our lead 2 plus in aqueous form plus 2 electrons is being converted to lead solid. So this one is a reduction reaction which is actually happening at the cathode. So as we can see, our lead 2 plus is being reduced to lead solid by the addition of 2 electrons there. So our lead 2 plus is acting as an oxidizing agent. Right? So now let's go to question 8.4. The initial reading on a voltmeter connected across the electrodes of the above cell is 1,53 volts. Identify metal X by calculating the standard reduction potential of the unknown metal X. Right? So what we understand is on that question 8.4, when we want to calculate the electrode potential of a cell, we know that we're supposed to have our electrode potential of our cathode minus the electrode potential of our anode. And we are given that our electrode potential of our cell is 1,53 volts, and the electrode potential of our cathode, which is the electrode potential of this particular reaction, straight from the standard reduction potentials, we know that the electrode potential for this particular reaction is minus 0,3 volts, right? And now we want to subtract the electrode potential of our anode, which is X, right? So now if we take our minus 0,13 volts to the left hand side, it becomes positive. So we're going to have 1,53 volts plus 0,13 volts, and that one will give us minus the electrode potential of our anode. If we add this one, we are going to get 1.66 volts is equal to minus the electrode potential of our anode. Dividing by minus 1 on both sides, we are going to actually have our electrode potential of our anode is equal to minus 1.66 volts. So if we are going to actually find from our standard reduction potentials the reaction which is the half cell which is this particular electrode potential, we see to that it is that one for aluminium. So we can actually conclude that the unknown metal X is actually aluminium, right? And this one can also agree with our oxidation reaction. Why? Just because from our question you can see that our S is being converted to X3 plus. So aluminium can also have an ion of aluminium 3 plus. So this one is actually a correct answer, right? If we go to question 8.5, it says write down the balanced equation for the net or overreaction taking place in this cell. Omit the spectator ions. Remember, we said that our spectator ions, these ones they actually watch a reaction taking place, and as a result they will not participate in the reaction actually. So what we are having is we can find them in the reactants as well as in the products. So at the end of the day we are going to leave our spectator ions, right? And then now we want to find the balanced net reaction. So what we are going to do is, in our question 8.5, we are going to have that reduction reaction which we have already written, that is our lead being converted, lead 2 plus being converted to lead solid, and this one is a reduction reaction. And we are having now that one for the oxidation of our aluminium to aluminium 3 plus aqueous ions plus 3 electrons. This one is an oxidation reaction which is actually taking place at the anode, right? And this one is a cathodic reaction, right? So what is going to happen now is that we are going to actually balance our electrons. So we have 2 electrons, then we have 3 electrons. So in order for our electrons to be equal, we are going to actually multiply this one by 3 and we are going to multiply this one by 2. So that is all the terms which we have in this particular reaction. We are going to multiply by 3. And then if we are going to actually write the overall reaction now, what we are going to have now is we are going to have our 2 aluminium solid plus our 3 lead 2 plus will give us 2 aluminium 3 plus in aqueous form, right, plus 3 lead solid. So this one now is our overall reaction, which we call a redox reaction, right? Now let us go on to the next question, which is 8.6, which says how will the initial voltmeter reading be affected if the concentration of the electrolyte in the X solid X3 plus half cell is increased? Write down only increases, decreases, or remains the same, right? The question is saying how will the initial voltmeter reading be affected if the concentration of the electrolyte in the X3 plus half cell is increased, right? So as if we are going to actually increase the concentration of our aluminium 3 plus in our initial voltmeter reading itself is going to be affected, in the sense that this one is a product, and as a result, if we are going to increase the product, it will favor the backward reaction. So therefore we see to it that we have a decrease in the voltmeter reading which we are going to actually get, right? Why? Because we actually get our electrode potential of our cell is equal to the electrode potential of our cathode minus the electrode potential of our anode. So if we have an increase in our anodic reaction in our aluminium 3 plus, which is being formed, so consequently we have a decrease in our initial voltmeter reading. So let us go to question 8.7. 8.7 says write down the value of the reading on the voltmeter when the cell reaction has reached equilibrium. Remember, at equilibrium, our rate of our forward reaction is equal to the rate of the backward reaction, which means to say that at equilibrium, the rate of the electric potential of our cathode will be equal to the electric potential of our anode. Therefore, the electric potential of our cell itself is going to be equal to 0. So our answer there is for 8.7. Our voltage itself is going to be equal to 0, right? Thanks very much for listening to this particular revision of our question number, our fifth question, which we have in our examination type questions. Right? Enjoy your listening. Right? Thank you.